Welcome everyone. Question number 177. Consider the following statements. Statement 1. Welded structures are usually lighter than riveted structures. Right. Because welded structures generally do not need a gusset plate or any other splice plate, which leads to lighter in weight. Statement 2. Welding allows the arrangement of structural components in such a manner that the joint provides maximum efficiency. Right. Welding joint provides the maximum efficiency. Statement 3. During welding, the members do not get distorted. No, during welding, due to heating and cooling, there may be expansion or contraction into the member, which leads to structural distortion. B is right answer. Question number 178. In the figure 10.21, sigma 1 and sigma 2 are the maximum and minimum principal stresses. In order that the resultant stress on the plane AB is root over of sigma 1 plus sigma 2 by 2 square plus sigma 1 minus sigma 2 by 2 square. The value of theta should be. Know the formula for resultant stress. R is equal to root over of sigma n square plus tau square. Sigma n is the normal stress and tau is the shear stress. Question. The resultant stress R is equal to root over of sigma 1 plus sigma 2 by 2 square plus sigma 1 minus sigma 2 by 2 square. That means normal stress sigma n is equal to this value and the shear stress tau is equal to this value. We know the formula for normal stress. Sigma n is equal to sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 into cos 2 theta. And if cos 2 theta is equal to 0, then sigma n will be equal to sigma 1 plus sigma 2 by 2 as per the question. So cos 2 theta equal to 0, 2 theta equal to 90 degree and theta equal to 45 degree. We also know the formula for shear stress is equal to sigma 1 minus sigma 2 by 2 into sin 2 theta. But as per question, sigma tau is equal to sigma 1 minus sigma 2 by 2. And to make that, sin 2 theta must be equal to 1. So sin 2 theta equal to 1, 2 theta equal to 90 degree and theta will be equal to 45 degree. Option B is right answer. Question number 179. 4 vertical columns of the same material, height and weight have the same end conditions. The buckling load will be the largest for a column having the cross section of. We know the formula for buckling load or crippling load. P is equal to pi square EI by LE square. E is the Young modulus of the column material, I is the moment of inertia of the column section, and LE is the effective length of the column. And as per this formula, we can write the crippling load or buckling load P is proportional to moment of inertia I, and I section has the maximum moment of inertia as maximum material is distributed to the far ends from the bending axis. So I sectional column will have largest buckling load as compared to others option given in the question. B is right answer. Question number 180. If all the dimensions of a piezometric bar elongating under its own weight are increased in the proportion of m:1, then the total elongation will increase in the ratio. We know the formula for self elongation of a piezometric bar. Del is equal to WL square by 2E. L is the length of the piezometric bar and E is the Young modulus of the bar and W is the weight of the piezometric bar. And as per this formula, we can write del is proportional to L square. So as per the increment of the dimension of the piezometric bar, length nu will be m times the previous length L. So L nu will be equal to ml, and the new elongation del dash will be equal to m square L square. So del by del dash will be equal to 1 by m square, and del is to del dash will be equal to 1 is to m square. And B is right answer. Number 181. Consider the following statements. If two planes at right angles carry only shear stresses of magnitude q, then the statement 1, the diameter of the Mohr circle would equal to 2q. Right. Statement 2, center of the Mohr circle would lie at the origin. Right. Statement 3, principal stresses are unlike and have magnitude of q. Right. Statement 4, angle between the principal plane and the plane of maximum shear would be equal to 45 degree. Right. Option D is right answer. So as per the statements of the question, the Mohr circle is drawn here. Diameter of the circle is equal to 2q Center lies at the origin 0 0, and principal stresses are plus q and minus q. They are equal in magnitude but unlike in direction, and the angle between the normal to the principal plane and normal to the maximum shear is 90 degree in Mohr circle, but in actual the value will be equal to 45 degree. Question number 182. A bar of square cross section is subjected to a pull of 10,000 kg if the maximum allowable shear stress on any section is 500 kg per centimeter square. Then the side of the square section will be maximum shear stress tau max will be equal to sigma by 2. Sigma is the direct tensile stress, which is equal to P by A. P is the actual tensile load and A is the cross sectional area of the bar. Now say X is the side of the bar. As the bar is square in cross section, the area will be equal to XX square. And from the question we have got the value P is equal to 10,000 kg and maximum shear stress tau max is equal to 500 kg per centimeter square. If we put the value in this formula, we will get xx square equal to 10 centimeter and x is equal to root over 10 centimeter. Option B is right answer. Question number 183. According to Tresca, yield locus is a hexagon. Option C is right answer. 184. The principal stresses at a point in an elastic material are 1.5 sigma tensile and sigma by 2 compressive. If the elastic limit in a simple tension is 2000 kg per centimeter square and the Poisson's ratio is 0.30, then the value of sigma at the failure would work out to be 1000 kg per centimeter square according to the. So as per question, sigma 1 is equal to 1.5 sigma 2 is equal to sigma, and sigma 3 is equal to minus 0.5 sigma, and sigma y is equal to 2000 kg per centimeter square, and Poisson's ratio mu is equal to 0.30. As per maximum shear stress theory, tau max is equal to sigma 1 minus sigma 3 by 2 equal to sigma y by 2. We have got all the values, so putting it in the equation we get sigma is equal to 1000 kg per centimeter square. So this perfectly matches the target value. So the governing theory will be maximum shear stress theory. Option B is right answer. 185. A beam of simply supported at the both ends of length L carries two equal unlike couples M at the two ends. If the flexural rigidity EI equal to constant, then the central deflection of the beam is given by. So by double integration method, the governing equation will be equal to EI d square y by dx square equal to minus M, and after first integration the equation becomes EI into dy by dx equal to minus mx plus c1, and boundary condition will be at x equal to L by 2 the slope dy by dx will be equal to 0. So after putting this dy by dx equal to 0 and x equal to L by 2 in this equation, c1 will be equal to ml by 2. Next, after the second integration of this equation, the equation will become EI into y equal to minus mx square by 2 plus ml x by 2 plus c2. Here the boundary condition is at x equal to 0, the deflection will be equal to 0. So the value c2 will be equal to also 0. Now after putting all the value, c1 value, c2 value and x equal to L by 2, because at L by 2 there will be maximum bending moment, will be equal to ml square by 8 EI. Option D is right answer. M is number 186. If the crushing stress in the material of a mild steel column is 3300 kg per centimeter square, Euler's formula for crippling load is applicable for slenderness ratio equal to or greater than. We know the formula for Euler's crippling load PCR is equal to pi square EI by L square. E is the Young modulus of the column material, and I is the moment of inertia of the column section, and LE is the effective length of the column. Now we also know moment of inertia I is equal to a k square. A is the cross sectional area of the column and k is the radius of gyration. Lambda is the slenderness ratio, which is equal to LE by k. LE is the effective length and k is the least radius of gyration. So After putting lambda equal to this and I equal to a k square into this equation, PCR will become y square e into a divided by lambda square. PCR by cross sectional area equal to the crippling stress is less than equal to crushing stress of the material. So by putting the formula, the lambda will be greater than equal to pi into root over of E by sigma crushing. Young modulus is equal to 2 into 10 to the power 6 kg per centimeter square, and sigma crushing given in question 3300 kg per centimeter square, and pi is equal to 3.14. Lambda slenderness ratio value will be greater than equal to 79.25, which is nearly equal to 80. Option D is right answer. Question number 187. Which one of the following pair is not correctly matched? We know the formula for crippling load PCR by Euler's is equal to pi square EI by L square, and for pin end column condition, effective length LE is equal to L. So the crippling load PCR will be equal to pi square EI by L square. Now if the column is fixed end condition, then effective length will be equal to 0.5 L. So the crippling load PCR will be equal to 4 pi square EI by L square. Now if the column is in fixed free condition, the effective length LE will be equal to 2L. So the crippling load value PCR will be equal to pi square EI by 4L square. And if the column is in fixed pin end condition, the effective length LE will be equal to L by root 2, and the crippling load PCR will be equal to 2 pi square EI by L square. So from calculation it can be said option D is not correctly matched. 188. The resultant cuts the base of a circular column of diameter D with an eccentricity equal to D by 4. The ratio between the maximum compressive stress and the maximum tensile stress is the value maximum compressive stress sigma C will be equal to load P by cross sectional area A into 1 plus 80 by D. E is the eccentricity and D is the diameter of the circular column, and maximum tensile stress sigma T will be equal to P by A into 1 minus 8E by D, and eccentricity E will be equal to D by 4 for no tension condition. And if we make the ratio sigma C by sigma T, the ratio will be equal to 3. Option A is right answer. Question number 189. A 3-hinge parabolic arch rib of an L and crown rise H carries a uniformly distributed superimposed load of intensity W per unit length. The hinges are located on two abutments at the same level, and the third hinge at a quarter span location from left hand abutment. The horizontal thrust on the abutment is. These 3-hinge parabolic are subjected to uniformly distributed load W per unit length. Suppose RA RB is the reaction at these two ends A and B respectively, and H is the horizontal thrust at two ends respectively. Now as this is a 3-hinge parabolic arch, so by taking only the left part from the point C, summation of moment at point C is equal to 0. So RA into L by 2, so the moment will be equal to RA into L by 2 in clockwise direction minus the load value minus WL by 2 into the distance, half the distance L by 4, minus the horizontal thrust H into the vertical distance small h, which is also in anti-clockwise direction, is equal to 0. And after doing the calculation, capital H will be equal to WL square by 8H. Option C is right answer. For 190, a shaft is subjected to a bending moment M and torque T. The equivalent bending moment M equivalent on the shaft is given by. The formula for bending stress for a shaft subjected to bending moment M and torque sigma B will be equal to 32 M divided by pi d cube, and shear stress will be equal to 16 T divided by pi d cube. M is the bending moment, T is the torque to which the shaft is subjected, and D is the diameter of the shaft. And according to the maximum principal stress theory, the bending moment produces the same maximum tensile stresses as the combined actions of bending moment and torque. So maximum principal stress sigma 1 will be equal to sigma B by 2 plus sigma root over of sigma B by 2 square plus tau square. And if we put the value of sigma B and tau in this equation, sigma 1 will be equal to 16 divided by pi d cube into within bracket M plus root over of M square plus T square. This is equation number 1. M equivalent bending moment equivalent bending moment is defined as the bending moment that produces same maximum stresses, same maximum bending stresses sigma 1. So equation 1 will be equal to equation number 2, equating 1 equal to 2. M equivalent will be equal to M plus root over of M square plus T square by 2. Option D is right answer. Question number 191. Consider the following statements for a rectangular footing of length L and breadth B applied with load P as shown in the figure 10.22. 1. The stresses developed at points A and D are equal due to geometric symmetry relative to load location. Statement 2. The stress developed at point B is maximum because the point is closest to the application of load P. Statement 3. The stresses developed at the point B and C are compressive. No, while the point B is highly compressive as the point is close to the load P and C is the farthest corner, it will undergo tensile stress. So this statement is wrong. Option B is right answer. Number 192. A 2 meter long of bar of uniform section 50 mm square extends 2 mm under a limiting axial stress of 200 Newton per millimeter square. What is the modulus of resilience of the bar? Length of the bar given equal to 2 meter, that means 2000 mm. Area of the bar is equal to 50 square millimeter and extension of the bar is equal to DLL equal to 2 mm and limiting axial stresses sigma is equal to 200 Newton per millimeter square. So modulus of resilience UR will be equal to, by formula, sigma square by 2E. We will determine the value of E, Young modulus. We know the formula for Young modulus E equal to sigma into L divided by del L by Hooke's formula. So by putting the value of sigma L and del L in this formula, E will be equal to 2 into 10 to the power 5 Newton per millimeter square. Modulus of resilience UR will be equal to sigma square by 2E. So if we put all the values, UR will be equal to 0.10. Option A is right answer. Number 192. If E equal to 2 into 2.06 into 10 to the power 5 Newton per millimeter square, an axial pull of 60 kN is suddenly applied to a steel rod 50 mm in diameter and 4 meter long, causes an instantaneous elongation of the order of diameter of the steel rod is given D equal to 50 mm and length of the steel rod is equal to 4 mm. So area will be equal to pi d square by 4 and the value will be equal to 1963.5 millimeter square. So the steel rod is subjected to a pull of 60 kilonewton and Young modulus for the steel rod is equal to 2.06 into 10 to the power 5 Newton per millimeter square. So static elongation del LS will be equal to PL by AE, and if we put all the value, del LS will be equal to 0.594 mm. But for instantaneous elongation, del L will be equal to 2 into this elongation del LS. So 2 into 0.594 equal to 1.19 mm. Option A is right answer. 193. If two springs of stiffness K1 and K2 are connected in series, the stiffness of the combined spring is. Option A is right answer. Question number 194. A thick cylindrical pressure vessel of inner diameter capital DI and outer diameter capital DO is subjected to an internal fluid pressure of intensity P. The variation of the circumferential tensile stress Py in the thickness of the shell will be. According to Lehm's theory, for thick cylinders, the circumferential or hoop tensile stress Py at any radius r is given by the formula Py equal to A by r square plus B, where A, B are constants determined by the boundary conditions. At the inner radius, r will be equal to Ri, the stress is at its maximum, and at the outer radius, r is equal to Ro, the stress is at its minimum. Since Py varies inversely with the square of the radius 1 by r square, the distribution is parabolic or hyperbolic and decreases from the inner surface to the outer surface. Diagram B correctly displays a non-linear decreases with the highest value at the inner boundary. So option B is the appropriate answer. Question number 195. A steel wire of 20 mm diameter is bent into a circular shape of 10 meter radius. If capital E, the modulus of elasticity equal to 2 into 10 to the power 6 kg per centimeter square, then the maximum stress induced in the wire is. We know the bending equation sigma max divided by y max equal to E by r. This is equation number 1. This cross section is the cross section of the steel wire of diameter 20 mm. So y max will be equal to this distance, this CG, the distance between the bottom and the CG of the cross section. So 20 by 2 equal to 10 mm, that means 1 centimeter, and the steel wire is bent into the radius into a radius of r equal to 10 meter, means 1000 centimeter. Young modulus of the steel wire is equal to 2 into 10 to the power 6 kg per centimeter square. So from equation number 1, bending equation, sigma max will be equal to E into Y max divided by R. By putting the value of E, Y max and R into this formula, sigma maximum will be equal to 2 into 10 to the power 3 kg per centimeter square. Option B is right answer. Question number 196. Given that for an element in a body of homogeneous isotropic material subjected to plane stresses epsilon x, epsilon y and epsilon z are normal strains in x, y and z direction respectively, and mu is the Poisson's ratio, the magnitude of unit volume change of the element is given by. The unit volume change, also called volumetric strain for a small element undergoing small deformation, is given by the sum of the normal strains in the three orthogonal directions. So option A is the right answer. Question number 197. A steel cube of volume 8000 cc is subjected to an axial to an all-round stress of 1330 kg per square centimeter. The bulk modulus of the material is 1.33 into 10 to the power 6 kg per centimeter square. The volumetric change is, we know the formula for bulk modulus K is equal to stress by volumetric strain. So volumetric strain means del V by V, and we have got the value of bulk modulus equal to 1.33 into 10 to the power 6 kg per centimeter square, and the volume of the cube is equal to 8000 cc, and the stress value is equal to 1330 kg per square centimeter. So by putting the value of them into this formula, del V will be equal to 8 cc. A is right answer. 198. In terms of bulk modulus K, modulus of rigidity C and Poisson's ratio can be expressed as, option C is right answer. 3K minus 2C divided by 6K plus 2C. Question number 199. The cross section of the bar is subjected to a uniaxial tensile stresses P. The tangential stress on a plane inclined at theta to the cross section of the bar would be. A bar under uniaxial tensile stress P experiences normal stress sigma x is equal to P, sigma y equal to 0, and tau xy is equal to 0 also. So the tangential stress on a plane inclined at theta to the cross section of the bar, tau theta, would be equal to tau x minus tau y divided by 2 sin 2 theta plus tau xy cos 2 theta. So by putting the value of sigma x, sigma y as tau xy in this formula, tau theta will be equal to P sin 2 theta by 2. Option A is right answer. Question number 200. Consider the following statements. Statement 1. On planes having maximum and minimum principal stresses, there will be no tangential stresses. Correct, because principal planes are defined as the planes of zero shear. Statement 2. Shear stresses on mutually perpendicular planes are numerically equal. This is the principle of complementary shear stresses. So statement 2 is also correct. Statement 3. The maximum shear stress is equal to the half the sum of the maximum and minimum principal stresses. No, it is equal to the half the difference between the maximum and minimum principal stresses. Option B is right answer.